Hi, everyone. Welcome. My name is John Seymour,
And I'm Azim Atil.
and our talk is called Your Voice is My Passport. We both do detection and response engineering at Salesforce.
Okay, so let's get into it. So we started to see that voice is starting to be used very widely as authentication. In fact, voice authentication or voice recognition is kind of a machine learning problem. And so with the advent of machine learning, we've also seen that voice quote unquote authentication is starting to become very ubiquitous. Now, when I say voice authentication, I think most people immediately think of Apple Siri or Google's Assistant. Both of these are services that run on your phone, and they're programmed to unlock when the target utters a pre-programmed sentence. So, okay, Google for Google, and hey Siri for Apple. Now, I do want to note here that neither Google nor Apple ever use the word authentication to describe their service. And in fact, you can only unlock a subset of your phone's features using your voice. We suspect that it's because both of them are aware that this might be brittle. All right, so here you have an example of Schwab Bank. Now, Schwab Bank actually does claim to do authentication. In fact, you can unlock everything about your account using just your voice. And funnily enough, the way that this works is after you've registered, you need to say the sentence at Schwab, my voice is my password to unlock. Now, password, not passport, but nevertheless, it's amazing that the irony is lost on them. And finally, here's an example of speaker recognition or speaker authentication as a service. So this is Microsoft's Speech API, and they also, in fact, do claim to offer this as an authentication service. All right, so as you may have guessed by now, our goal is to break voice authentication, but we want to do this with minimal effort. So let me be precise about what I mean here. By breaking voice authentication, I mean gaining access to a service that is currently deployed by impersonating somebody. And by minimal efforts, we actually mean three things. So the first, whatever solution we come up with should not require tons and tons of compute. Now, this is because deep learning tasks and machine learning tasks tend to require lots of computation resources. And so we're thinking maybe like a commodity desktop, not like a server farm. Second, our solution should finish in some reasonable amount of time. Again, deep learning tasks tend to require lots and lots of time to finish. And so we're thinking days or weeks, not months. And then finally, realizing that solution should require little or no data science expertise.
Awesome. So if you haven't seen the movie Sneakers, it's a hacker classic from the early 90s. It's also quite a bit relevant to our talk. So in it, the heroes actually need to bypass a voice authentication system, and they do so by social engineering their target to say specific words in the passphrase. So we actually have a clip here.
Clear all the way up to the man trap.
My voice is my passport. Verify.
Right. So here's how you do it. So let's start with the initial idea, right? In Sneakers, basically they record the words for the passphrase from the target by using social engineer. In practice, this is hard for multiple reasons. First, the people you'd really want to impersonate are probably generally pretty busy people, right? You think CEOs, politicians, things like that. They may not actually care about sitting down in a room with you. Second, I don't know if you've ever tried to get someone in a conversation just to say the words, hey Siri. You're probably going to draw suspicion to yourself if you try to get them to say certain words of specific authentication phrases. But even if you could manage to do the above two, authentication prompts are actually very smart, right? Like they randomly change sometimes. Whatever you record, when it comes time to authenticate, it might be, not the phrase that you actually need the target to speak. However, luckily, we have a service to stop this. There's this thing called text-to-speech. It's also a machine learning-based solution. Basically, you give the system a bunch of audio and text and of a particular person, and it produces new audio for you. It also, it's a huge area of research. There's a NIPS workshop dedicated to it. So NIPS is a pretty prestigious machine learning conference. And there's a lot of improvements going on in the field. There's a lot of implications that this technology actually introduces, right? Consider the impersonation of a politician, right?
This is a dangerous time. Moving forward, we need to be more vigilant with what we trust from the internet. That's a time when we need to rely on trusted news sources.
Right. So that was actually Jordan Peele generating audio and video for Barack Obama, and that came out of BuzzFeed. This should convince you that this technology has become pretty widespread, and just think of what you could do with a huge AI research lab backing you. In our case, we're going to focus exclusively on using text-to-speech to bypass voice authentication. So we really do not care about the quality of our audio. In fact, it could sound garbage to a human. As long as it bypasses the speech APIs, we're golden.
All right. So the essential idea behind all text-to-speech systems is that you give the algorithm some text and it generates the equivalent audio representation of that text. So for example, that audio representation could be MEL spectrograms, which you can kind of think of as the waveform corresponding to some text. Now, the model learns the mapping between words and this audio representation, or more precisely between character sequences and the audio. And the way that it works is that you give the model your input, which is transcribed audio. And then after many, many iterations, the model learns this mapping that I've been talking about. Now, there's a few things that I want everyone to focus on. The first is that generally, voice models, text-to-speech systems are trained on a single person's voice. Now, this is generally true, but it's starting to change. In fact, John is going to talk about why. The second thing I want you to remember is that all deep learning systems in general, and voice in particular, require tons and tons of data. And so the academic consensus is that you need around 24 hours of really high quality audio in order to get reasonable output. And note the emphasis on high quality. So the last thing I want you to remember is that there are two widely available open source data sets that would have high quality audio and over 24 hours of data. The first one is LJ Speech and the second one is Blizzard. We'll be getting to these later, but the only difference between these is for the first one is a recording of a female, the other one is of a male.
Cool, right. So we have this idea and we want to do a proof of concept. So actually there's this company called Lyrebird, and one of their missions is basically to bring awareness to the implications of this sort of technology. It was founded by several of the pioneers in sort of text-to-speech and machine learning research. And basically they also actually host a lot of similar videos to the Jordan Peele one we showed earlier. As a demonstration to the general public, they've actually set up a service where you can generate your own voice given some recordings. And so the actual steps are pretty simple. First, you go to Lyrebird, you create an account. You basically record yourself in a room saying 30 sentences or more. These sentences are determined by Lyrebird in advance, and they're the same for every user. And then you provide a target sentence via text, of course, that you want Lyrebird to generate. It only takes a few minutes to generate audio. And sometimes there's some degradation of quality. It's also finicky with a lot of accents, for example. But we actually did a quick proof of concept using Siri and Microsoft's speaker recognition's public beta. And we did not test on Schwab or Google Voice for this. So first, what we do is we train Siri or MSR's public beta to recognize our voice. Then we generate the target passphrases using Lyrebird, and we see if it works. So we actually have a video of our proof of concept here. Basically what it does is it goes through, we train the voice, then we show, it works, it doesn't work for Azim, it doesn't work if you say the wrong thing, and then it works for our generated audio.
My voice is stronger than passwords. My voice is stronger than passwords. My voice is stronger than passwords. My voice is stronger than passwords.
So obviously it works.
This is a test and should be rejected.
And it rejects bad speech.
My voice is stronger than passwords.
It rejects the wrong person.
My voice is stronger than passwords.
And so that was actually audio generated by Lyrebird, and notice it actually gets through. So this is fun. However, there's actually some, cool. So this proof of concept is actually limited, right? So first it requires specific utterances from the target. So as that falls back basically to the same problem that we talked about with sneakers, right? You actually have to social engineer a target to say particular sentences. It's simply unlikely that an attacker could actually obtain such recordings from the target. Though this does mean that the Lyrebird database, as well as speaker recognition authentication databases in general, might actually be useful targets to attack. It also worked very well for me. It didn't work as well for Azim. We think it's due to accents and ethnicities of speakers. But to demonstrate how a real attack might work, we actually turned to the state of the art in text-to-speech generation.
Okay, so one of the things that I mentioned early on is that our driving principle is to make this as easy as possible, right? And so we naturally turn to open source models, open source text-to-speech models. Now there are several open source text-to-speech models that are available. Two of the most famous ones are Tacotran, which is by Google, and WaveNet. Now, WaveNet tends to do very well. It outputs very realistic human-sounding audio. But the problem with WaveNet is that it tends to be, it requires that you tune it significantly. So what I mean by that is, like, there are these tons of input parameters to WaveNet, and you need to tune each of them. So as an example, to some of those parameters, there's the fundamental log frequency, the phenome duration, there's like these tons of linguistic features. And all of these require domain expertise in order to tune for your particular scenario, right? And this is exactly the kind of thing that we would like to avoid. And so we turn to Tacotran, which is by Google. So Tacotran simplifies this process greatly because it kind of takes this feature tuning part out of the equation. So here is an example of the system architecture of Google's Tacotran. So on the bottom, what you have, it basically has two parts, the one on the top and the one on the bottom. One on the bottom is a recurrent sequence-to-sequence feature prediction network that has attention, and it generates. So it takes as input your raw transcribed audio, and it generates these MEL spectrogram frames. The one on the top is a modified WaveNet, and it is conditioned on those predicted MEL spectrograms, and it actually generates the waveform audio corresponding to that. Now, Tacotran kind of works on the principle of superposition of two neural networks, which is just this fancy way of saying the combination of two neural networks. So the first one is kind of responsible, the one on the bottom is kind of responsible for generating this visual representation of sound frequencies, and the one on the top kind of turns that into actual audio. Now, the really good news is that you don't really need to know any of that for this to work. You can just take Tacotran off the shelf and use defaults, and it'll tend to work.
Awesome. So we have a couple audio examples here for different versions of Tacotran and WaveNet. So actually, this is going to be Tacotran V1, this first audio clip. That came out actually in April 2017 is when Google released it.
Scientists at the CERN laboratory say they have discovered a new particle.
Right. So you can hear, a lot of perturbations in the audio, but this is what happened in December 2017 with Tacotran version 2. And so basically think April to December, this is how much the audio quality is increased.
Generative adversarial network or variational autoencoder.
Right. And obviously they're putting quite a bit of work into it if you know about like Google Duplex and things like that. So finally, just for completion's sake, we have an example of WaveNet here.
A man dying of liver complaint lay on the cold stones without a bed or food to eat.
Right. So you can definitely hear that it's better quality than Tacotron V1 and similar quality to Tacotron V2 just from hearing it. Again, it takes a lot of basically munging of features and things like that.
Okay, so let's talk about data. Now, data is essential to any machine learning model, and I've already mentioned that you kind of need lots of it for this particular task. So where can you get this data from? So now, if your target is someone who does lots of public talks, let's say, for example, John, you could maybe scrape this from YouTube or some other public source. I want to remind everyone what the quality and the quantity of data is important, right? And then what you need to do is transcribe this data. And then finally, you need to chunk it. So the chunking is necessary because of the way that these open source models work. They require that the input be broken down into sentences. And that's basically it. So when we initially started doing this, we thought that we could use Google's Cloud Speech API and kind of kill two birds with one stone. The way that the Cloud Speech API is supposed to work is that you give it audio, and it gives you not only the transcript of that audio, but also the start and end times for each word in your audio. Unfortunately, we could not get it to work really well with the audio that we scraped, John's audio that we scraped off of YouTube, which is not to say that the speech API is not very good. In fact, when you give it really good high quality samples, it is really good. But it tends to have lots of problems with noise, and when you're getting your data off some public source, chances are that it's going to be noisy. It also tends to have these weird issues with like natural pauses in human speech, like or So what we ended up doing was we had to manually transcribe all our data. Now, this is not so bad because we only had to transcribe about 5 to 10 minutes of it, but you see how this kind of limits the time that you can put into it. So finally, chunking audio turned out to be relatively easy. We just used FFmpeg and kind of split those sentences on silence, and that does a good job of just separating the speech into sentences. Okay, so I mentioned that both the quality and the quantity of data is important. Unfortunately, when you scrape data off some public source, there's going to be some parts of it that are noisier than others. So applause, for example, is not going to play very well. And so we had to cut that out. And what I mean to say is that we had to sub-select the best samples from our audio. The data itself is also very limited, right? So at this point, we're dealing with about like 5 to 10 minutes of data, of high quality data. And transcribing is also very time intensive. And we already know that you need large amounts of data, right? I mentioned that you need 24 hours to do very well. Well, 5 to 10 minutes is not nearly enough. Our solution to that problem is something called data augmentation.
Right. So there's a few ways to augment data. One of the ways that we found works very well is by shifting pitch. So if you slow down and speed up audio, one of the side effects of that is the pitch actually changes. And we can abuse this to basically generate new samples that sound similar to the original examples, but still are new examples and we can train on. There's tons and tons of libraries available for this sort of thing. We use PyDub. And to actually make this a little bit rigorous, what we did was we measured how far we could slow down or speed up the audio, and it'd still be accepted as valid authentication for Siri, in fact. So what we did was we recorded me saying, "Hey Siri," we slowed it down, we sped it up, we recorded how far we could actually change that pitch, and what we found was basically we could slow it down to 0.88 times the original audio speed, and it would still get accepted. Beyond that, it would start getting rejected. Similarly, on the other side, we could speed it up to 1.21 times, and it would still get accepted. But of course, your mileage may vary for the exact parameter, right? It's probably different for every single person, et cetera, things like that. So notice this actually fixes our original issues, right? It multiplies our original training data set by about 30 times. as well as actually, we only need to transcribe about a 30th of the data. And since transcribing is a very manual process, that's, we can be a little more lazy. However, this does introduce one issue, right? And that's a potential overfitting. So if you only, take like 1 out of every 30 sentences someone says, you're probably going to miss some sentences or some words that they might say, some phonemes. So you need to actually be very careful not to overfit in the represented words that you actually scrape, because the model is actually being trained on just a small subset of what the target might say. So this amplifies our data by about 30 times, but if you actually think 5 to 10 minutes times 30 is still nowhere near the 24 hours that most text-to-speech algorithms actually need to train. So our models were still producing complete garbage, and shifting pitch basically ended up not getting us all the way there. So calculating based on open source data sets, in order to hit the 24 hours, we need to actually transcribe 1 hour of data. And that's actually, again, considering the high qualityness that you need, that's actually still an issue, not even considering the whole limited vocabulary issue. So we actually turned to the idea to domain adaptation or transfer learning in order to augment our data set further. And basically, how this works is you initially train on one data set, and say like one of the open source data sets we mentioned earlier, you get a good model. And then you basically take that model, you exchange the data set that you used to train with the target's data set, and you continue to train a bit with the new data set. And so basically what we think is the model initially learns to speak and adapts sort of like the pitch, the accents, things like that, and with the new data as you continue to train. And we think this actually works because of the sort of layered approach of neural nets, right? If you think like sort of the base layers are the things that get the fundamental aspects of what it means to like translate audio to characters or characters to audio and words to sentences and things like that. And the higher layers are, we think, what actually learns like pitch and things like that. There's still a lot of variance in the effectiveness here. Sometimes the model actually converges within one epoch or one view of the new training data set. And sometimes it actually takes a couple days to converge. But we actually have a demo of our transfer learning model. And so here's an example of when we trained on Blizzard and we set a passphrase and our final, basically the Blizzard model saying it and then the final model. Again, I want to emphasize that we were not targeting human quality, we were targeting the API quality.
I am going to make him an offer he cannot refuse.
So that was Blizzard, right?
I'm going to make him an offer he cannot refuse.
And so that was transferring over to my voice, and that was completely generated using Tacotron V1, not V2, right? So the epochs actually vary, but this one took about 2 days to train the initial model on Blizzard, and then 1 overnight to train to adapt to my voice. So extremely small in deep learning terms. And we weren't even using like heavy GPUs and things like that. That actually audio quality is good enough to break some of the APIs that we mentioned earlier. So the approach actually works, which is kind of scary and surprising. It's not as consistent as even Lyrebird here, but the added advantage is it doesn't require specified speech in advance. We just grab stuff off YouTube, train the model, and then generate new speech. Overall effort, it took us about a month from conception to completion of this project. And more effort would just make it better. You could tweak more parameters. There's so many parameters we could have tweaked, or we could have added much more data. But 5 to 10 minutes of a target's data is good enough to do quality, to break APIs.
All right, so I think we've kind of thrown some stuff at you guys, so I kind of want to take a step back and recap everything. So the steps that one would need to take from start to finish to impersonate a target. So you start off by scraping data from the target, some publicly available source, I don't know, maybe YouTube. You subsample, you select the highest quality samples from your audio, transcribe and chunk that audio. Then you need to do data augmentation. So you first do that by shifting pitch, and then you train a general text-to-speech model on some open source data set. replace that general training model with the target data, and you finish training. So at this point, you should be able to successfully synthesize your target's voice. So now I kind of want to talk about the rest of the space, so machine learning for offense, and kind of put our work into perspective. So we've grouped these works into two arguably very broad buckets. The first one is attacks on machine learning systems, and the second one using attacks are attacks using machine learning systems. So our work is kind of like fairly in the center of both of these things. I want to add that the separation is not nearly as clean as we're making it out to be, but we feel that it makes it easier to think about and reason about these things. So the first thing are adversarial attacks, right? Now, adversarial attacks are the hottest topic in machine learning security right now. In fact, the two words tend to get used synonymously. And the way that they work is you have to specially craft your input to a machine learning system in such a way so that your input ends up getting misclassified. So let me give you an example to make that clear. So say you have some image recognition system, right? And you have a picture of a dog. So you would carefully change some pixels in that picture, the picture of a dog, give it to the system, and it would be misclassified as, say, I don't know, maybe a panda or something. Now, the main point here is that the unaltered picture and the altered picture are indistinguishable to the human eye, but the machine learning system, for whatever reason, misclassifies it. Now, the security implications of something like this should be immediately obvious, but let me just give you an example, or the canonical example that everyone always gives. So think of a self-driving system, right? Now, you have a stop sign that's been intelligently tweaked. So to a human eye, it still looks like a stop sign, but the machine learning system or the self-driving system would misclassify that as a yield sign. Now, as far as voice and adversarial attacks go, the most famous of these works is actually hiding hidden commands into benign sounding audio. So for example, you would have a phrase like, okay, Google, hello, or something like that. But the system would actually misunderstand that to mean send an email. Now, this is obviously a very attractive thing, a very sensitive thing as well. But the problem with this method is that it's currently very brittle. So the next thing you have is something called poisoning the well. Poisoning the well is kind of is similar to adversarial attacks in the sense that you craft your input specially, but your aim is to kind of poison the model, as the name kind of implies. Differential privacy is kind of the flip side of that. So by carefully observing the output of your model, your intention is to deduce something about the data that went into the model.
So again, this categorization isn't as simple as we're making it out to be, but another sort of category is attacks using machine learning systems. And so we've seen a lot of different things. For example, pen testers are starting to try to use machine learning techniques to basically increase the effectiveness of their attacks. But specifically want to draw attention to things like phishing and spear phishing, where you can actually generate, natural language to a specific target based on like their social media profile or things like that. In the past year, actually, we've also seen the first, what I'd consider like large-scale machine learning-based attack in the form of deepfakes. So if you don't know about deepfakes, it's basically there was an app created that allows you to basically transplant the one piece or like a headshot of one person onto the body of another person in a video or photo. And actually, people started using it for not safe for work and pornographic use cases. And then finally, robotics and social engineering, we also want to bring attention to it. And there's a lot of cool research in this area as well. We're going to see more research into how machine learning can be used and abused in the future.
Okay, so let's talk about some mitigations. Now, the way that most modern speaker authentication systems seem work is that they're programmed to recognize only a specific passphrase, right? In fact, it turns out that speaker recognition with an unknown vocabulary is hard, right? The other problem is that even if you're doing standard speaker recognition with some passphrase, saying it out loud somewhere actually means that you're giving out your password, right? So what we suggest instead is multi-factor authentication, and to be more specific, to treat voice authentication as only a weak signal on top of an existing multi-factor authentication system. So as an example, let's say you have some MFA system that requires tokens, maybe RSA tokens or some kind of passphrase. So instead of typing it out, the user would say the token out loud. And what this would add on top of the system is just another weak signal, like I said. Now, I want to emphasize here that speaker recognition and speaker authentication are two very different and separate problems, and they should be treated as such. So on this slide, we have maybe 2 examples of something you could use to detect an attack like ours. On the left-hand side, you have an example of a system that tries to detect computer-generated audio. On the right-hand side, you have a device that kind of detects these neuromuscular features, and the idea is that this way you can predict that the person speaking is in fact a human. Now, we've kind of thrown these out there, but we want to emphasize that we think that this is an arms race, and so you should treat this with the skepticism that it deserves.
All right, so what all have we basically found out while we did this project, right? So first, speaker authentication and speaker recognition are 2 different problems, and recognition should be treated only as a weak signal for authenticating. Second, speaker authentication can be broken if the attacker has speech data of the target and knows the authentication prompt. Third, although most text-to-speech systems require about 24 hours of speech to train, you can actually reduce this requirement drastically by using things like data augmentation and transfer learning. In fact, transfer learning is a very useful technique to know generally if you're doing data science. It works in a lot of different use cases. And finally, just in conclusion, it's relatively easy to spoof someone's voice. This is only going to get easier over time, and you can do it in a few days with open source tools. Just as a final note, actually, after we submitted this talk to Black Hat, Google ended up publishing a paper in June of 2018 on very much a similar idea, right? Transfer learning from speaker verification to multi-speaker text-to-speech synthesis. We just want to sort of emphasize here that we're not the only ones researching in this area. There's a lot of different groups and people researching text-to-speech, how to make it better, and how to use it for basically attacking speaker authentication systems. So this field is actually growing at a very alarming rate, and we should start figuring out what to do about it now. And with that, actually, that's the end of our talk. Just want to ask if there are any questions.
Quick question here. My question about your models that you use. Were you considering any adversarial examples when you were doing the training? So if the models that you already have actually include...
Can you speak up, please? I can't hear you at all.
I think this is off. All right, perfect. Question is about adversarial examples. So for your machine learning models that you used, those are the public models, obviously, that they're available. But how were you able to actually identify if this models has not been modified? You know, so in deep neural networks, for example, there is an adversarial attack on the models that you can use for your training. Were you considering those models or no?
So your question is, how did we know whether the model was...
They were attacked or no? So consider that you have a classifier for machine learning, and the classifier objectively has been modified. So whenever you're doing your training, actually your training is compromised. Were you considering that in this case?
All right, so I think I might understand the question. And so the question is, in our training process, basically, did we do anything to sort of detect adversarial or sort of poisoning the well or attacks on our models that we generate here, right?
That's right.
Okay, cool. So the answer here is we actually didn't consider those right now. We're actually taking the attacker mindset in terms of if we wanted to break, sort of speaker authentication or speaker recognition systems. So in our threat model, the attacker actually has control over, this open source model that exists. I mean, obviously, sort of adversarial techniques can be useful. And obviously, like Carlini and everyone have sort of demonstrated that you can use adversarial techniques to generate, good quality sounding audio. we chose to use the simpler approach of just using text to speech because it works better, for example, over the air. So you can actually play this over the air and break, a lot of the APIs that exist now.
So then how would you protect against liveliness detection? I think you actually mentioned that because, they are, for example, Siri doesn't do that. There's no way for Siri to distinguish between a recorded voice and a real voice that is actually happening at the same time. So if there's a liveliness detection, probably the attack that you're having right now will fail.
Yes. So if I understand you correctly, basically your point is that people will always be able to use adversarial training to get around sort of like these speaker authentication systems.
That's right, yeah.
Yeah, so that's totally 100% true, and we definitely view that as like a possibility slash something that will happen. Our goal here was to show it's even simpler than that right now.
Good, thanks.
No problem. All right, cool, awesome.